CCIX, Gen Z, and OpenCAPI, and we have one person to talk about each one, and I'm going to spend very little time myself talking to keep things moving, but what we're going to do is we're going to do all three presentations, which are short, they're like 5 to 7 minutes, to give you kind of an overview, and then we'll do questions at the very end of all three, because I think some of the questions that you ask are going to end up being kind of appropriate for all three, so I think it's better to first get everybody's overview, and then we'll do the questions. So first we have Millind Mittal, is that how you say it?
Yeah, that's right.
And he's a Senior Director of Architecture at Xilinx. And I actually have different sized bios for each person, but I think it's actually better to just get to the slides, and the bios are on the website if you want to know more details, right? I think that's what's important. So you can come up here or sit, whichever you want to do, and there's your thing. Is it switched on? It's just this top thing here. Wait for the green light, and you're good. Yeah.
Yeah. Okay. Okay. Hello. Yeah. So I'm going to talk to you about CCIX. This is cache coherent interconnect for accelerators. The idea here is that currently accelerators are really viewed as a peripheral device connected through an I/O bus, right, like PCIe, right? And as you looked at some use cases today here, and I'll a little bit mention about them further, but essentially the idea here is that now it makes sense looking at the needs of the platforms to evolve these peripheral devices instead of being just an I/O device where they have their private memory and there's an overhead of data movement, to make them more like a NUMA socket, like it says, CC NUMA socket, essentially you can call it, where they become peers to the processors. So that's the idea behind CCIX. CCIX is an open consortium, open standard consortium, and goal here is to really standardize this CC NUMA interface, you can call it, and then basically broadly work towards adaptation of that interface and truly create a heterogeneous platform capability in the industry. So let's look at what the trends are that it's trying to address. So first is really, we talked about how the need for augmenting processors capability is increasing. There are lots of workloads that require lots of computation. There are workloads that they're time sensitive, essentially require quick processing, fast processing. Then also there are workloads that require operating on very large amount of data, lots of computation, lots of storage that you need, right? Broadly speaking. So now if you look at all of the trends here, essentially the other thing that as I already mentioned, what you want to now really start to address is saying that just doing all the intelligent processing on the processors. And also, it was mentioned just a little bit earlier, where the state has been so far that all the memory that you need for computation has to be attached to processor sockets. That's becoming quite limiting. So essentially now what's happening is that there's trend towards making accelerators smarter. Part of that is they are also running software stack. They are becoming self-hosted. Like as you understand in Amazon, you offload even hypervisor to a NIC card. The other part is that you want to now start thinking about expanding the resources of processors. You do it in two different ways, that you say that memory, you can have system memory that is managed by the operating system, not only connected to the processor sockets, but can also be connected to an accelerator device. So accelerator device memory is not private anymore. You can expand it out to that. An operating system can manage it. In that scenario that somebody was mentioning earlier, that one interesting paradigm now is to do near memory processing. Essentially, you're really coming up with much more efficient processing flow. So when you expand your memory, first of all, you're just getting more memory by going to this accelerator attached memory. But this also, if you have accelerator attached memory, it's really giving you real estate there to do some intelligent processing near memory. So it becomes a very capable platform for doing near memory processing, along with memory augmentation. Then the other thing is compute augmentation, where accelerators have always been used as offloading device. You do some computation offload, but I think what is very interesting is looking forward is to say it's more than just offloading a function. You actually start thinking about offloading a thread, which is a macro function or some macro processing unit, and really make it efficient, this collaborative environment. And that requires then having an interface between the accelerator and the processor that allows you to do fine-grained data sharing. You basically can operate just like two threads on two cores, do data sharing in the shared memory. That's the paradigm you want to enable even with accelerators. The other trend is that basically people have talked about this decomposable platforms, or also people talking about pooling of resources, where you can actually borrow resources from another node, so on and so forth. So there is a lot more data access across nodes. And here, RDMA is a very good paradigm for low latency, but also starts to make sense to enable a paradigm where you can actually do synchronous access. And in certain cases, that is quite beneficial. Here, what CCIX is trying to do simply is bringing out the memory accesses out of the processor to the accelerator. We are not going in the space of creating a fabric, but this becomes a very good landing space to bridge over to upcoming fabrics, essentially. The accelerator becomes a good landing space for bridging over to the fabrics. So these are some of the trends that CCIX is trying to address. It's a pretty healthy ecosystem, and it has grown very rapidly. It was formed in 2017. And you may have seen already that there are products out there already implementing CCIX. A company ARM-based solution was announced by Huawei, announced a processor which implements CCIX. There are other processor designs in flight that implement C6. Xilinx, I work at Xilinx. Xilinx already has a product out in market, FPGA, that implements this interface. And it has a very strong roadmap of enabling FPGAs based on C6. We have a very healthy ecosystem represented by all different types of vendors. And the next thing is that our base spec is ready. Designs are already happening. For more information, please go to the website, c6consortium.com.
Good. Thank you, Millind.
Thank you.
And yeah, please. Thank you. So next we have Kurtis Bowman from Dell, who's going to talk to us about Gen Z. There you go. And your slide should just be the next click.
Excellent. All right. So I'm very happy to be here today to talk to you a little bit about Gen Z. It's a consortium that formed just over 2 years ago and has grown from about 12 members to now a little over 60. We're at about 65. And the membership includes everything from processor vendors to silicon, software, OS, connectors, everything we need to really have a vibrant ecosystem. And we've done a number of demonstrations now. We've been at Flash Memory Summit the last couple of years, and we've been at Supercompute to show off how you do memory pooling in a fabric-based environment. And also have a number of companies that are working on IP. And so people like IntelliProp have IP available. PLDA has some IP in development. And then we've got silicon vendors that are starting the designs of the actual silicon needed to implement this. As a full consortium being very open, we put everything out on our website, so you'll find the full specs that we've released out there. We now have 9 released specs that include mechanical, protocol, PHY specs. And we also have a couple of drafts out there so the public can take a look at them and give feedback into what we're doing. The reason we want to do this is we believe that, as you look on the picture on the right-hand side here, that we need a fabric that allows you to get outside the server or a storage box and get to components that you can both tier memory with and compose systems with. And so as you look at that picture, we need a very high bandwidth, very low latency fabric where we're looking at maybe 100 nanoseconds to get outside the server, 30 nanoseconds to get through a switch, and then your latency is dependent on the type of memory that you might be using in those storage systems. You can also compose in different types of accelerators, FPGAs and GPUs. Big piece here is it's multi-pathed. So we have a highly reliable system. You've heard a lot of people talk today about, I don't want to get stranded persistent memory. What happens when my server goes down, if I have persistent memory in there that somebody else is looking for, it's also gone. And I don't know about you, but I can't have persistent fun if my memory's gone away. So we need to have a way to get multipath outside the box to these external pieces. Also, under the compatibility piece, a lot of people have talked about, hey, I don't need OS changes, or I don't need application changes. Gen Z is very much in favor of that. But much like you've heard, you can start that way, but you really want to start moving toward changes that optimize for persistent memory out on some sort of a fabric. Another piece that Gen Z brings is an opportunity for innovation. One of the big challenges that we have, and we actually heard some questions about it earlier, is, hey, if I've got a memory bus that sits between the processor and memory, that processor is only going to know how to speak a certain amount of languages, right? So it only knows how to speak to maybe a DDR4 or coming DDR5. That means as new memories come out, if they have slightly different interface needs, I can't talk to them, I need to wait for a processor spin. Gen Z says, no, take the memory controller and put it where it belongs, put it right next to the memory. And then use Gen Z as that link to get between the processor and the memory, so that it's very simple for you to change the memory on the outside. And it can be DRAM, or it can be any other type of persistent memory that we need. So if you need a more SRAM-like interface to your memory, it's available. If you need something that's completely unique to you, it's available. It also allows for that media controller to start to do some of the compute that was talked about earlier. So if I want to put simple things in there, it's just a command across the Gen Z interface to say, here's what I want some sort of compute engine to do that's sitting right next to my memory. And so this is the kind of thing that we're looking for as part of the Gen Z group, to be able to really enhance that in-memory compute. And then finally, one of the other problems it's solving is Gen Z is very similar to PCIe as the number of pins it takes. But it's actually running at a higher speed. And so what you get is you get a lot more bandwidth out of your CPU for a small number of pins. Right? If you look at DDR5 is going to be coming out as a good 50 gigabytes per second. It takes about 200 pins per interface. So as you go from 6 to 8 to maybe 10, your CPU continues to get larger and larger, and its needs on a system board start to take the place of where you want to put those DIMMs to begin with. Same thing is true of PCIe. As we go to Gen 4, we get to 64 gigabytes per second. We've got Gen Z coming out the door at 200 gigabytes per second, and it's got path forward to about 448. So when you start looking at the amount of bandwidth you get, it's on the order of 4 to 8 DDR5 channels and 3 to 7 PCIe channels. Really gives you the bandwidth you need to feed those cores that are being added to the CPU at a great rate. So overall, we think that Gen Z is a good answer for how you're going to need the compute to work tomorrow, and a great interface into persistent memory. We'd invite anyone to come in and join us on this effort and help us even define Gen Z a little bit better. So with that, I'll hand it off.
Thank you, Kurtis. Excellent. Okay, next we have Steve Fields, who's an IBM fellow, who's here to talk to us about OpenCAPI.
What is that noise?
I don't know. That was an interconnect on overload.
That was a drum roll. So we built OpenCAPI with a pretty simple, focused mission in mind of being a streamlined, low latency, point-to-point interface between a CPU and some other device, whether that's an accelerator device, an I/O device, a memory device. Kept the mission very focused on that usage model, that topology, so that we could create a very streamlined interface that was high performance and put a very low tax on the attached device design. OpenCAPI first showed up in products in Power 9 servers in late 2017, but OpenCAPI was architected not specific to the Power architecture, but with the intent that it's supportable under any CPU architecture. The attached device operates in an application's virtual address space, or potentially in multiple applications' virtual address spaces. We do that similar to what Millind described, so that all the communication overhead and the related software path length of communicating with the device through an I/O subsystem just goes away. You get the efficiency benefits of treating that device like another CPU thread. In OpenCAPI, we only allow the device to see a virtual address, never sees a physical address, and that is so that if we have a broken device or rogue device, we don't have to worry about the thing getting to unauthorized memory locations, causing system problems or security exposures, whatever. And that also then allows us to move as much of the complexity as possible of this attach up into the host CPU. All the address translation, the coherence management, all the architecture-specific things reside in the CPU. We did that for two reasons. One, there's a handful of people in the world who build microprocessors and a lot of people building accelerators. So if we can move that circuitry out of the accelerators and move that validation problem, the state space, out of the accelerator into the processor, do that validation a handful of times and simplify the lives of the accelerator designers, and we get to a broader accelerator ecosystem over time. So we've talked quite a bit in the past about OpenCAPI for accelerator attach. I wanted to talk a little bit about OpenCAPI as a memory interface. We've done a fair amount of work leveraging a couple of decades of IBM experience on building external memory buffers and disaggregated memory controllers and such to enable the OpenCAPI architecture to allow an external memory controller attach with about 5 nanoseconds of latency penalty compared to a direct attach RDIMM. 5 nanoseconds is a small price to pay when you get 4 times the bandwidth per pin. If you look at a Power 9 scale-out processor with 8 channels of DDR4, we have about 1,800 pins invested in that memory bandwidth on the bottom side of the module. And imagine someday if we want to double that bandwidth, I don't want to put close to 4,000 pins of memory on the bottom of my module. So it's a big way to get more bandwidth, less cost. But kind of as Kurtis described, we'd also get the benefit of packaging the media controller with the media, so we can get to a technology-independent memory slot, allow system bandwidth and flexibility to mix and match technologies, do a multi-tiered memory solution that optimizes for the needs of a particular application. So that's OpenCAPI as a memory interface. OpenCAPI consortium is at opencapi.org. The specs are there. The interface IP is available to any OpenCAPI member. Have at it. Thanks.
All right, thank you very much. Okay, so these mics are on, and so we can ask questions now, and we have our microphone runner out there. Everybody's favorite interconnect, there's one way in the back. The last row back there.
So one of the most interesting things I saw recently was and I don't know if this is correct, so please correct me if I'm wrong. This goes to Steve. Is the physical PHY for OpenCAPI? It's BlueLink, right? So can you talk a little bit about what because you're obviously, you had in the last generation support on top of PCIe physical PHY, and then you went to BlueLink. Can you talk a little bit about some of the latency benefits? Because obviously the bandwidth is higher than PCIe Gen 4, right? But can you talk a little bit about the latency advantages of BlueLink, and if you guys are actually intending to opening that up for so it could be on FPGAs and whatnot?
So the latency benefit was not so much driven by maybe indirectly. The latency benefit is because it's such a streamlined protocol relative to PCI. No byte rotations. It's just very, very simple, very straightforward. And we do get round trip, we get a couple hundred nanoseconds of latency when we compare what we can do on an OpenCAPI access versus a PCI access. In terms of opening it up, it is the OpenCAPI standard. It's open, available for people to use. Anyone can make a product out of it by being an OpenCAPI member. I don't know. So the physical PHY is just 802.3. It's standard Ethernet technology. I mean, Gen Z's used the same thing. So there's no magic in the PHY itself. Yeah.
Good. Other questions? We're making our microphone runner's getting his exercise here. I hope you have your step counter going.
So I have a question for Kurtis. For this Gen Z interconnect, is this similar to what we had like a decade ago when we had a Northbridge talking to the memory DIMMs, or is the memory controller itself actually attached to the DIMM?
The memory controller in the vision it would be attached to the DIMM or the memory device. Yeah, so more akin to maybe some sort of RDIMM that had more smarts to it, if you will.
And how will that affect the cost of each DIMM? Since the more DIMMs you add, of course, you're just going to have a lot more memory controllers.
Yeah, and most DIMMs that are in enterprise class systems already have some sort of buffering on them, right? And so it's adding to that buffer. The cost of the silicon itself is not really that large, and so I don't think it'd have a material impact on that cost.
Got it. And I guess are all semiconductor companies such as Intel and AMD on board with this type of idea, or?
We do have a number of them. You mentioned Intel. Intel is one of the companies that has not joined yet, but we continue to encourage them.
Okay, thank you so much.
Okay, Jim on this side over here.
Mr. Brookwood. Thank you, Nathan Brookwood again. One of the issues when you move the logic onto the DIMM is power. That was one of the things that really killed the fully buffered DIMMs in the last generation. So how does Gen Z handle power? What kind of increment does it impose on the overall design?
Yeah, I mean, a lot has changed, fortunately, since fully buffered DIMM. And so with the reduction in power rails, as far as voltage goes, I don't think you're going to see that being a lot more power hungry than the current DIMM form factors that we have spec'd out.
Oh, thank goodness. Glad to hear that.
Good. Let's see. Did I see? Yeah, Jim, there's another one just further down there.
I'll ask that last question, or another question a little bit more pointedly, which is the common theme seems to be let's move the memory controller out of the processor. I guess certain large people in the processor business might have an opinion on that. But more practically speaking, is that a permanent barrier, or does it come down to the point of there's enough Moore's law breakdown and such that we need the real estate anyway? And so is there room for some flexibility on that?
I'll start with this. So the issue isn't that we need to free up space in the processor as much as two things. One, getting the bandwidth that we need to sustain our performance growth over time. It is going to put a lot of pressure on the frequency of the interfaces, and if the frequency of the interfaces are driven by or limited by heavily loaded DRAM nets, we're spending an awful lot of pins on our processors. But then the bigger issue is there are a lot of companies out there with memory technologies in the oven that'll each have their own cost, capacity, latency, endurance, all their own attributes. And we need a server ecosystem that lets us take advantage of all of that. So as long as we're designing memory controllers and CPUs that are only tied to DRAM and we're trying to do nutty things to shoehorn other technologies into a DRAM-like slot, we're going to be challenged in terms of exploiting that ecosystem.
Kurtis, Millind, if you guys want to add it.
Can you go?
No.
Okay, so I'll just say, so I think C6 view is there are three reasons to consider this. Definitely it's not about replacing DIMMs from the processor. It's about augmenting the processor resources. And the drivers are really if you want more bandwidth, basically, or more capacity, more memory. Like as you do in memory database processing and so on, you want just more memory. This is one way to do that. Second is if you want to do near memory processing, where you want to do some custom processing. So this allows you a platform to do that custom processing when you augment the memory outside the processor. And the third one is really these different memory technologies that you want to adopt into your platform without changing processor.
Good. We still have time for one or two more. Yeah, go ahead.
Hello. I just want to ask about software. So it seems that these platforms are opening up a new space of how servers and components can be used in the server. But I imagine that there's no freelance, so I guess software complexity might go up, right, in these scenarios. Have you guys evaluated that, or do you see any gaps in current programming models or languages, or any research direction?
I'll start. So I believe there's opportunity for more complexity, but it doesn't start that way, right? So it comes in and gives you opportunities to grow your footprint, but use your applications that you have ready to go today, use the OSs that are available today. Then this morning we've seen lots of efforts by lots of companies where they're going to enable more and more features, and that will give you the opportunity to expand your use of persistent memory across these interfaces.
And some of this will drive more complexity, some of it will actually drive less complexity. You know, example would be an accelerator talking to an application in the virtual address space is much simpler to program to than talking to that same accelerator through an I/O subsystem. But the existing base of software is built around the traditional I/O subsystem, so while we'll get to a simpler spot eventually, it's going to take work to get there.
And maybe I'll add one more point is that, I mean, this NUMA paradigm is well understood paradigm today. So if you have, basically that's how you have to think about it, right? Second thing is, you know, having multi-threaded application is understood as well. So those are the types of models you want to use, but the fact is heterogeneous, right? It does add to the complexity, but some of it can be hidden from the application. But, you know, from the NUMA type of paradigm, you would either the application is NUMA aware already, is able to deal with those latencies, or if not, then this is the paradigm you will need to think about. Yeah.
So as a SNIA NVM programming twig person, are any of you aware of any problems with our current programming model for persistent memory that would with your interconnects, or would you expect it to work the way we have it defined? Because if there are problems, we want to know about it. Yes. But I personally don't see any. Right, I think it fits very
I don't
nicely.
think there are any.
I just wanted to make sure.
I was going to say, there's nothing that jumps off the page, but it's something that I will ask our consortium to dig into a little bit.
Please do. Sure I think it's, you know, to benefit all of us is to make sure it works across all these interconnects. Mm-hmm. Okay, I think that wraps up our time, on time. So let's thank everybody on our panel.